Welcome back to part 2 of our curve sketching using the derivative topic. So in the first video, we learned how we would sketch a graph like this, and we covered the maximum and the minimum turning points or stationary points. And we saw that these stationary points are stationary because the gradient at these points is 0. So at the end of that video, we touched on the fact that in between these 2 points, we're going to have something called a point of inflection. So let's continue looking into that. Now, the gradient function is what gave us these stationary points. We were looking at what's happening with the gradient. Now, if we review what the gradient function is, if we start off with a function, f of x, and we want the rate of change of that function, how is this function changing, we get f dash x. And we said it's either increasing, decreasing, or stationary. But what about if we cared about the rate of change of f dash x, right? Well, that would then be the second derivative. So in essence, this is the rate of change of the rate of change of the function. So the second derivative is the rate of change of the rate of change of this original function. So if this is increasing or decreasing, are we increasing at an increasing rate or are we increasing at a decreasing rate? Now I know that just sounds like a bunch of words, so let's look at the graph. We know that a function is increasing when f dash x is greater than 0. So when we have a positive gradient, we know the function is increasing. So why don't we look at here, at this point here, we've got a negative gradient. So I know at this point here, I've got negative gradient, so my function is decreasing. As my function continues to decrease, the jump between every x value would look something like this. But do you see how the slope is getting steeper and steeper, but at a faster rate? That means we are decreasing at an increasing rate. So everything up until this point here, I would say we are decreasing at an increasing rate. We're decreasing at an increasing rate. But what starts to happen here? Well, I can see that I have still a negative gradient, right? My gradient is still negative, so I'm still decreasing. I'm decreasing, but it starts to slow back down. So I'm decreasing at a decreasing rate. All right. Decreasing and decreasing, increasing rate, decreasing rate. This second part here, the the second derivative, is called the concavity. So write that word down, that's a very important word. Concavity. So the concavity looks at the change of our change, If a graph is a maximum, like this, we say it is concave downwards. If a graph is a minimum, we say it is concave up. Now, how do I remember this? See how this looks like a U? U for up. Because we go from a concave down, up here, where we have a maximum, to a concave up down here, the concavity changes. We go from down to up. That is this point there. Now, what is the rule for concave down? It is when we have f double dash x is less than 0, because we have a increasing, we're decreasing at an increasing rate on that side. And when we have concave up here, we have f double dash x is greater than 0. All right, just like earlier, when we go from less than to greater than, we have f double dash x equals 0 in between. That between point is the point of inflection. So the rule then states to find the point of inflection, the point of inflection happens when f double dash x is equal to 0. That is the point of inflection there. There is no change. So we're still decreasing at this point, right? At the point of inflection, because we know it's there from this first derivative, but there's no increasing rate or decreasing rate. It's just flat, it's decreasing. So at that point of inflection, is found when our second derivative is equal to 0. So let's find it. Let's come back to this graph. We've already sketched these points. I'm going to clean everything up and we'll keep going. So if we come back to this graph that we're trying to sketch, we know that we've got a maximum point here at 0, 3, a minimum point at 2, 1, and there is a point of inflection somewhere in between. So how do we find that? Because it's an actual point that we need to be showing on our graph. So we said the rule. We know that the point of inflection happens when the second derivative is equal to 0. So let's come back to our function again. We had our first derivative, y dash was 3x squared minus 6x. And then we had our second derivative now, that becomes 6x, that becomes minus 6. Okay, so when the second derivative is equal to 0, let's solve this. Factorize, not even, I can just say 6x is equal to 6. Dividing both sides by 6, I cancel, and I get x is equal to 1. So it appears, and I say appears because we have something else left to do, it appears that we have a point of inflection at the point x is equal to 1. So really quick, when x is equal to 1, we get 1 minus 3 plus 3 is just 1, so y is equal to 1. So the point here is 1, 1. Now, what did we say happens on either side of a point of inflection? We said that this is concave down, a maximum point is concave down, and a minimum point is concave up. So we said that there needs to be a change of concavity. The same way that I needed to test these 2 points to show, yes, there is a max here and there's a min there, I need to show and I need to test that there is a concavity change. So the way we do that is very similar to how we did the first derivative test. We're going to do something with the second derivative now. So we have x and double dash. We know what's happening at the point x is equal to 1. So let's test on either side. When, let's say we have 0.5 and the point 1.5. Okay, what is my concavity at these 2 points? So when x is equal to 0.5, we sub that into our second derivative, and we get 3 minus 6 is minus 3, so we get a negative, and so we know this is when f double dash x is less than 0, and this is when it's greater than 0. So we get a negative number, so we can say that this is concave down. So it looks like that. When it's 1, we just get 0, okay, so we get nothing. And when it's 1.5, we get 9 minus 6 is a positive number, so it's concave up. Perfect. We go concave down, no concavity, concave up. Because there is a change of concavity here, we can conclude now, yes, there is a point of inflection at the point 1, 1. So my graph will end up looking something like this. That is how I would sketch, ignore the very yucky section here, but that is how I would sketch y is equal to x cubed minus 3x squared plus 3. So this is my max, this is my point of inflection, and this is my minimum. All right, we're very close to finishing. We've got one more thing to cover on. If you watched the first video, you would have seen that I showed you that there was 3 types of stationary points. A minimum, a maximum, and something that we called a horizontal stationary point. Now the technical correct term for this is a horizontal point of inflection. Let's look at sketching one and finding it. So the last part of understanding curve sketching using the derivative is what I called earlier the horizontal point of inflection. So this is really the combination of 2 things. It's both a stationary point and a point of inflection, and I'll show you what I mean. So let's look firstly at the gradient at specific points. So right here in the middle, at that horizontal point of inflection, we can see that the gradient is flat, right? So we can say that f dash x here, the gradient is 0. Let's look at the gradient, say on the left-hand side. We have a positive gradient, so we have f dash x is greater than 0. But let's look at the gradient here. We also have a positive gradient, so we can see f dash x is also greater than 0 on this side. So it doesn't look like a traditional stationary point where we have, say, something like a minimum where the gradient changes on either side, but we still do have a 0 gradient in the middle. Let's now start looking at the concavity. How much and how quickly, how is the gradient changing? So over here, I've got a steep positive gradient, and it starts to slow down. I mean, it's still positive as we get closer and closer. So what it looks like I have here is it looks like I have a concave down. It looks like I've got a minimum for this side here. So we can actually say that f double dash x on this side, because it's concave down, we can say it's a max, so it's less than 0. Right? So we can say f double dash x is less than 0. All right, let's see what's happening if we look at the right side. So I've got a positive gradient, but as I go along, it gets steeper and steeper. So this is a decreasing rate, but this is an increasing rate. So it's almost like I have a minimum point there, which would be that f double dash x is greater than 0. So what's happening here? Like I said, I've got a 0 gradient. I have the fact that f dash x is equal to 0 because my gradient is stationary. But I also have a change in concavity. I'm going from concavity less than 0 to concavity greater than 0. So that must also mean that I have a concavity equal to 0 at this point. So that gives us the rule that a horizontal point of inflection happens when the first derivative is equal to 0 and the second derivative is equal to 0 at that specific point. That is how you find your horizontal point of inflection. So let's do that now in one big question and see if we can sketch it. With this graph, you'll be bringing everything together from video 1 and video 2. So we will have a stationary point, a point of inflection, and a horizontal point of inflection. Let's just give it a big crack and see how we go. First thing I know is that my stationary points occur when my first derivative is equal to 0. So my first derivative y dash will be 4x cubed minus 12x squared. I set that equal to 0, so I get, I can factorize out a 4x squared. So 4x squared, I'm left with x minus 3 is equal to 0. So I can say x equals to 0 or x is equal to 3. So these are my 2 points. Now when x equals to 0, I clearly get y is equal to 0. And when x is equal to 3, I get y is equal to negative 27. So let's test these two x values and see what kind of stationary points they are. Remember, there can be a max, a min, or a horizontal point of inflection. So let's see. When x is equal to 0, the first derivative, I will test the points minus 1 and 1. Subbing in minus 1 into my first derivative here, 4x cubed minus 12x squared, I'm going to get a negative gradient. Subbing in 0, I get 0, and subbing in 1, I get 4 minus 12, I also get a negative gradient again. So this isn't what we'd normally expect. Normally we'd be expecting something like that, but it clearly is looking like a horizontal point of inflection, just the other way around. There's two types. I've only shown you that one, but they're the same thing, just flipped. So it looks like I have a horizontal point of inflection. Now I can't be certain. I need to do a couple more things later. We'll come back to that in a second. Let's keep testing this next point. So x is equal to 3. On either side, I'll test the points 2 and 4. Subbing in 2, I'm going to get 4 times by 8 minus 12 times by 4. That is going to give me a positive number. Subbing in 3, I'm going to get 0. And subbing in 4, I'm going to end up with a negative number. So I can see here that this point 327 is very clearly a minimum turning point. So 3 negative 27 will be somewhere around here. This is 3 negative 27, and I know that is a minimum. Okay, so we've done everything we can so far using the first derivative. Let's keep going and let's look at the second derivative, s double dash x, and we're going to set that equal to 0 to find any points of inflections. The second derivative here is going to be y double dash equals 12 x squared minus 24x. Now I know my point of inflection is when that equals to 0, so I'm going to set that equal to 0 and factorize out the 12x. I'm left with x minus 2 is equal to 0. So x is equals to 0 and x is equal to 2. Now I already know when x is equal to 0, y is equal to 0. But when x is equal to 2, y is equal to negative 16. Okay, what have I just shown? I have shown that I've got a stationary point and a point of inflection at the point x is equal to 0. So it's very clearly starting to look like I have a horizontal point of inflection. The last thing to do is to show and be confident, yes, this is a point of inflection. Once we've done that, we can bang on confirm horizontal point of inflection. So how do we do that? Remember, same sort of test that we've done here, but now we're testing for the concavity. So at -1 and 1. Okay, when I sub in -1 to here, I get 12 plus 24, I get a positive number, which is greater than 0. So I've got a concave up. When I sub in 0, I get 0. When I sub in 1, I get 12 minus 24, which is a negative number, so less than 0. So I get concave down. Amazing. I've shown a change in concavity, therefore it's a point of inflection. I've shown it's a stationary point, so it's both. So I now know I have a horizontal point of inflection at the point 0, 0. Last thing is x equals to 2. Let's see what's happening when x is equal to 2. So 2, let's try the point 1 and 3. Well, when I know when it's 1, it looks like that. When I sub in 2, I have to get 0. When I sub in 3, I'll get positive 36, which is greater than 0. So again, I've got concave up, change in concavity. So at the point 2, negative 16 here, at 2, negative 16, I've got my point of inflection. So horizontal point of inflection into a point of inflection into a minimum stationary point. That is how you would sketch this curve. Now I know there's a lot there, so take your time, let it all sort of sink in, go back and watch over the video if you have any questions. Let me know in the comments if you have any questions as well. Click that subscribe button and check us out on TikTok. We post the videos there every day, and I'll catch you in the next one.